Our last section, chapter 11, test using contingency tables. We're still working with chi-square, independence, and homogeneity tests. The assumptions, the data are obtained from a random sample. The expected value in each cell must be 5 or more. So just like we saw with our goodness of fit test, if we needed to have 5 or more in each category, same idea here, we'll have it in table format. So each cell must be 5 or more. Just like with our goodness of fit test, if the expected values are not 5 or more, you can combine categories if needed. So that's the same thing we did with our goodness of fit test. The test for independence, it's used to determine whether two variables are independent of or related to each other when a single sample is selected. So let's take a look at the first example. I just built an example in to the lesson this time. So if a study conducted as to whether there is a relationship between joggers and the consumption of nutritional supplements, random sample of 210 subjects is selected, and they're classified as shown in our table. At alpha is 0.05, test the claim that jogging and the consumption of supplements are not related. When you state your hypotheses, that's still our first step, your null hypothesis will always state something to the effect of the two variables are independent or not related to each other. They're either independent or not related to each other. Your alternative hypothesis will always state something along the lines that the two variables, one is dependent upon the other, or that they are in fact related to each other. To test our null hypothesis by using our chi-square distribution, we need to compute the expected frequencies, and when you do that, you're going to assume the null hypothesis is true. So you're going to assume that the two variables are independent of one another or are not related to one another is what you will assume. What a contingency table is a data arrangement for the chi-square independence test. You have R rows and you have C columns designated as R by C. So a lot like if you worked with matrices before, I know some of you might have worked with them. Some of you might have worked with them in Algebra 2. I don't know if everybody did or not. Some of you might not have ever worked with matrices before, and that's okay. Don't panic if you haven't. Each table value is called the cell value, and it's designated by its row and column position. So we have our first cell value, 1, 1. It's always rows, then columns. So the first number there designates the row it's in. The second number designates the column it's in. So we have our capital C here just for our cell value. It'd be row 1, column 2. Row 1, column 3. So it looks like a little ordered pair. It's just always rows by columns. And I don't know, this might be getting a little bit too old for you guys. If you've ever heard of RC Cola, that's how I always remembered these, rows then columns. I've had students in the past that have never heard of RC Cola. They remembered remote control, that it's rows then columns. That's how some people like to remember it. If you come up with something else that works, but those are the two that are most often used. Your degrees of freedom, a little bit different. It's not just as cut and dried as we take n-1 or n-2. You take your number of rows minus 1 times your number of columns minus 1. So this degrees of freedom just a little bit more involved than what we are used to. Oops. How you compute the expected frequencies for each cell. The first thing you need to do is find the sum of each row. So total up each row and find the sum for each column. And then you need to find the overall grand total. So find the total for each row and for each column. Double check my numbers, please. Double check me. That's what I came up with when I added those. Once you have those totals, to get your expected frequency for each cell, you have to multiply the row sum by the column sum and divide by the grand total. So here's what that would look like if we just write it out for the, let's say, the joggers who jog daily. Your row sum is 9. $109 times your column total of 52 divided by the grand total of 210. So it's your row sum. So for the daily joggers, the row sum is 109 times the column sum of 52 divided by the grand total. And when you round, you could round to the nearest, usually nearest hundredth is typically what you'll see. You can go more decimal places if you would like. So we end up with 26.99 for our daily joggers. So go ahead, just take a couple minutes and see if you can find the expected values for the rest of the table. I just like to, if I write them in the table, I just put little parentheses around to keep them separate, or you could circle them or put a box around them, your choice, just to designate those are the expected values, and the ones that are already in there were your observed values from the sample. Our next step will be to find our critical value. We need to use table G for that. It's always right-tailed, just like our goodness of fit test, always right-tailed. And then the degrees of freedom we see here again. Capital R is the number of rows, capital C is the number of columns. So number of rows minus 1 times the number of columns minus 1. So our degrees of freedom for our example, number of rows is 2, number of columns is 3. So our degrees of freedom being 1 times 2, which will just give us 2 for our degrees of freedom. Alpha at the beginning of the question, I know it was a couple slides ago, we said let's use alpha at 0.05. And so we need to use table G, degrees of freedom 2, alpha at 0.05. So table G, degrees of freedom at 2, alpha's at 0.05. It's always a two-tailed test. So again, just like with goodness of fit test, we don't have to worry about dividing alpha by 2, subtracting it from 1. We just use alpha as is. So our critical value will end up being 5.991. After we find our critical value, we want to find our test value. It's the same formula as we did for the goodness of fit test. Same exact formula, which is really nice for this. There's one little contingency there. When the degrees of freedom equal 1, some statisticians will say to use the Yates correction for continuity. We're not going to use that. I just wanted to make you aware that it is a possibility. Who knows how many of you will use these one day in a future course or career, so Just want to throw that little in there. Some statisticians, not all. So I just want to throw that disclaimer in there for you. So our formula, we had to add up our observed frequencies minus our expected. We squared each of those, and then we divided by our expected. Now you can, if you want to, I know we put these in our list last time. We can do that, but I want to show you how to use the matrices to get what you need for these. So if you want to, again, you can do all these. So we can start with the observed of 34 minus 26.99 and then divide by 26.99. Plus we can do 52 minus 60.73 quantity squared divided by 60.73. You could do that for each cell if you want to. You can do that for each cell if you want to. It's just the observed. It's just the observed from each cell minus the expected from each cell, that quantity squared, divided by the expected for that cell. So if you want to, in action, I'll go ahead and write those out here. I know some of you out there are going to prefer the formula to the calculator, so let me go ahead and finish this out. 23 minus 21.28 quantity squared divided by 21.28. Again, it's just the observed in the cell minus the expected for that same cell, quantity squared, divided by the expected for that cell. 65 minus 56.27 quantity squared divided by 56.27, and then we have observed of 18 minus 19.72 quantity squared divided by the expected of 19.72. If you do that, you end up with approximately 6.683-ish, somewhere around there. And again, I go out to the thousandths decimal place because that's what my critical value goes to. So this is an option for you. This is an option for you. I do want to show you, however, how to use a calculator to do these. To use the calculator, I know for the goodness of fit test, we entered all the observed values into list 1, all the expected into list 2. The contingency tables are actually a little bit simpler in the calculator. If you've never had to enter matrices in before, that's the part you're really going to have to focus on. Some of you I know have, some of you haven't. To enter in a matrix, go second, and then you hit the X inverse key. You'll notice the word matrix is right above it. You want to enter in all your observed frequencies into matrix A. In order to edit the matrix, you have to highlight edit on the far right and then hit enter on matrix A. Matrices, the dimensions are the same as with our contingency tables, rows by columns. So we have 2 rows and we have 3 columns. We have a 2 by 3, rows then columns. Then we have to enter in all of our observed. Enter in all of our observed values. So we have 34, 52, and you need to enter them in so they match the table. So all of your cells need to match up, table to your matrix. They all need to match. So the matrix you enter should look identical to the contingency table that you have. Should look identical. Once you have all of your information entered into matrix A, we go to Stat, Tests, and I always forget which letter this one is. And we just use, last time it was the goodness of fit test, this time we use the letter C, which is just the chi-square test. It's just the chi-square test. Press enter on that. Your observed values were in matrix A. And you might be thinking, Miss Golly, we didn't put our expected in matrix B. Don't we have to do that? No. When you put in the matrix for where your expected ones need to go, and you want it to be matrix B, you want to use matrix A and matrix B for these, when you put it in, that's where your expected values are going to go. You don't have to enter them in. That's where this test program will send your expected values. So our observed are matrix A, expected go to matrix B. We hit calculate. 6.682, I think we had 6.683 when we used the formula. There's your p-value. It also tell you degrees of freedom. So it will do everything for you. Now I know in the past I've shown you guys some programs on here that make things a lot quicker and simpler than using the formula, but some of you still choose to use that formula. That's okay. You'll get the same result as we just saw. The calculator, however, will speed things up tremendously for you with this. A lot less calculation. And if you want to see, if you go to second, and we go to matrix again, if you want to just go to edit and look at matrix B, there's all our expected values. So if for some reason you would need those specific expected values, they're right there in matrix B for you. So that will do everything for you. And we'll see that again. We'll do it. We have 2 more examples today. We'll use the calculator with both again to make sure you've got the hang of it. So let's go ahead and make our decision. Always right-tailed. Critical value is at 5.991. So test value is going to be somewhere in that shaded region, so we're going to reject. And our claim was that the consumption of supplements is independent from our jogging status. So that was our null hypothesis. Null hypothesis was our claim. So we're going to say there's enough evidence to reject the claim that the consumption of supplements is independent or not related to jogging status. Let's try out one more of these, and then we have one more test for this section involving some proportions. We have an instructor wishing to see if the way people obtain information is independent of their educational background. Survey of 400 high school and college students yielded the information below. We're going to use alpha 0.05, test the claim that the way people obtain information is independent of their educational background. So our first step is to write our hypotheses. Your null hypothesis is always the one dealing with the variables being independent, or if you want to see if they're not related to each other, that's going to be your null hypothesis. In this case, we're looking for independence. So our null hypothesis would say the way people obtain information is independent of their educational background. And then your alternative hypothesis then will state the dependence part. So the way people obtain information is dependent upon their educational background. critical values, just like goodness of fit test, we're right-tailed. We will use table G. Only difference is we have to find our degrees of freedom. Number of rows in this case is 2 minus 1 times the number of columns, which is 3 minus 1. So we get 1 times 2. Degrees of freedom will be 2. I'm just going to jot down again, alpha's at 0.05. And we're right-tailed. I just like jotting that information down. Take it or leave it. I like pulling it out of the question. So critical value, we need to go to table G for that. Degrees of freedom are at 2 again. Alpha's at 0.05. And we do end up with the same critical value as the last example. Just be very careful. Don't just now assume, oh, degrees of freedom are always going to be 2 because that's what it was for our 2 examples in class. It's dependent upon your number of rows and number of columns. Our 2 examples just happen to have the same number of rows and columns. And our alpha value was the same for both also. So just be careful. Don't just start assuming that it's always going to be 5.991. Just be careful of that. 5.991. So there's our critical value. Step 3 for your test value. I'm hoping that the calculator just appealed to a lot of you. If the calculator didn't appeal, I will show you again how you get your totals and show you again how to get those expected values. You need to add up every row and every column and get those totals, and then you also need a grand total. So if we add up the first row, 159 plus 90 plus 51, we have a total of 300. 27 plus 42 plus 31, we have a total of 100. The total for the first column is 186. 132 for the second column, and 82 for the last column. Our grand total is 400. Our grand total is 400. So if you want to use the formula to find each expected value, you have to take the row sum times the column sum divided by the grand total. Row sum times column sum divided by the grand total. So you can find all those expected values, and then for step 3, if you want to add up observed minus expected quantity squared divided by the expected for each cell, you can do that. I will let you use formulas. I'm not going to take more class time to show that, so if that's something that you choose to do instead of the calculator, I can help you more with that during work time if you'd like. I'm going to turn us to the calculator at this time. Let's go ahead and enter in to matrix A all of our observed values. So in this case, we had 159, 90, 51, 27, 42, and 31. Again, just take that extra little half second and make sure that your matrix exactly matches that table you're given of observed values. Then from there we go to stat, we go to tests, and it's letter C. So if you want to get there faster, you can press alpha and then look above the program key and you'll see there's a C there. That will take you to that test faster. Our observed values, always just put those in matrix A, have your expected go to matrix B. Just keep things nice and organized. We hit calculate, and our test value is at 21.347. If you wanted to do p-value method, you could. There's the p-value right there for you. Very quick, very easy to figure out. So let's record our test value. 21.347. If you need to draw the picture, you can. Critical values 5.991. 21.347 is definitely somewhere in that shaded rejection region. So we reject the null again. Our claim, we need to rewind. We forgot to actually state which one our claim was. They want to claim that the two are independent of each other. So our claim is our null once again. So there is enough evidence to reject the claim. That the way people obtain information is independent of their educational background. Now I chose these couple examples for one of the big reasons that the claim is in the null each time. I know that a lot of us, we get so used to there's enough evidence to support or there's not enough evidence to support our claim, but talking about supporting the claim only comes when the claim is the alternative. If the claim is in the null, and that's going to happen a little more often with our independence test, when the claim's in the null, when you go to summarize, it's about there being enough evidence to reject or not enough evidence to reject. Just be very careful on that one. I want to make sure we hit a couple of those again, just so we can make sure we know how to state that conclusion. Just be careful on your conclusion. Our final test for this unit, homogeneity of proportions. Very, very similar, except for now our samples are being selected from several different populations. When we were testing for independence and our goodness of fit test, all those samples were coming from just one population. Those samples were coming from one population. Now we're coming from several different populations. It's used to determine if the proportions of elements that have a common characteristic will be the same for each population. That's what we're looking for. So we're looking for some common characteristic. Will the proportion be the same for each of the populations? That's what you're trying to compare. This also uses a contingency table. So really, really similar to the test we just ran, but we're testing for something completely different. We're not looking for independence. We're looking to see if proportions are going to be the same for different populations. So we have a recent survey. 32% of Americans say they are very likely to become organ donors. A researcher surveys 50 drivers in each of 3 neighborhoods to determine the percentage of those willing to donate their organs. The results are shown here. At alpha 0.01, test the claim that the proportions of those who will donate their organs are equal in all 3 neighborhoods. So each neighborhood is seen here as a different population. So they want to know if the proportions are going to be equal for each of those neighborhoods. That's what we're looking for. So the first thing we have to do is state our hypotheses. And you guys are going to like these hypotheses much better than we've been doing for the last couple tests. They're not nearly as wordy. I know we're doing goodness of fit test, and now with our independence test, they get a little bit wordy. These we're going back to some symbols. There's 3 different, and here's where you have to pay attention, there's 3 different populations here. Your null hypothesis is going to depend on how many different populations you have. Do you have 2? Do you have 3? Do you have 4? Do you have 5? Because when you state your null hypothesis, you're going to state the proportions are equal, but you don't have to write it out in words. You just have to do P sub 1 equals P sub 2 equals P sub 3. And we're trying to show that they're equal, so that one's our claim. So you don't have to go through and write out that the proportion of organ donors in neighborhood A will equal the proportion of organ donors in neighborhood B and all that stuff. So you don't have to get wordy with these. But you do have to make sure, though, and yes, I will be picky come test time, that you have the right amount of proportions. So it's not going to be 3 every time. It's determined by how many different populations you have. That's what you need to look at. We have 3 different populations. Each neighborhood's a population. That's why there's 3 P's for this one. So just be careful. Then your alternative hypothesis, it does have words, but not a ton. At least one proportion is different. That's all you have to say. So the hypotheses for this particular test, not too bad. They're not as wordy as the last couple. Critical values, how we find those is not going to change at all. Degrees of freedom, still number of rows minus 1 times the number of columns minus 1. And now, yes, I realize now we've done 3 examples for this lesson, or this is our 3rd and final one, I should say. And yes, every time degrees of freedom have come out to be 2. That's just because we've had the same amount of rows and the same amount of columns for all 3. Your rows and columns can change. So degrees of freedom will not always be 2. I want to make sure that I make that clear, at least hopefully I am. Degrees of freedom 2. Alpha is different this time. We're at 0.01. Still always going to be right-tailed. Now I know that throws some people off because now we're seeing equal signs back in the null hypothesis. We're not dealing with anything but right-tailed. There's no inequality in the alternative to tell us different. So we're just sticking with right-tailed. So let's visit table G. Degrees of freedom still at 2. Now this time's alpha is at 0.1. 0.01, excuse me. Degrees of freedom 2. Alpha's at 0.01. There we go. So then our critical value is 9.210. So there's our critical value. Your test value is the same formula that we had for goodness of fit that we had for our test for independence. How you find the expected values, you have to add up your rows and your columns and get your grand total also. So your total for your columns, that's already given to you. That's at 50. So you have to add up the total for each row. So this total is 63. We have 87. And the grand total should be 150 because it says in the question they're going to survey 50 drivers from each of the 3 neighborhoods. So your total should be 150. So again, if you want to use the formula, you want to use the outright formula, you take your observed, that's the formula part. To get your expected values, same as it was with our independence test, row sum times column sum divided by grand total. Row sum times column sum divided by grand total. Now, if you look at these though, if all your column sums are the same, your expected value for that first row will be the same also. So my expected value for that whole first row is going to be the same. And that will also hold true for the second row. Every time we're going to do 87 times 50 divided by 150. So again, if you want to use out the formula, you want to complete the formula, observed minus expected quantity squared divided by expected, you find your expected values the same way as we just did for the test of independence. Same way. Row sum times column sum divided by the grand total. You would find that for each cell, and then you would plug everything into the formula that you need. Can we use our matrices just like we did for the test of independence? Absolutely. Is that what I recommend? Absolutely. Again, my concern is not can you plug and chug away in a formula and find all those values. My concern is can you state your hypotheses? You have to be able to find your critical value, and then let the calculator do the busy work to get the test value. It's just doing one step for you. The calculator is doing one step for you. You still have to be able to do the other 4. You have to be able to do those other 4 steps. So let's again turn our attention to the calculator. We go to second. It's the little X inverse key for matrix. Edit. Still have a 2 by 3. We have 28, 14, 21, 22, 36, and 29. And the nice thing is when you enter these values in, it's really easy. Again, just do that quick double check. Does my matrix match my table? Do I have the right values in the right spots? Stat, tests, alpha, program key gets me C, observed in A, expected in B. Our test value, 8.046. Now again, I know I kind of bypassed that formula a little bit today. I did talk about how to find expected values for each one, but if you're more interested in the formula than the calculator, I can help you out with the formula if that's something you'd rather choose than the calculator. I won't make you do the calculator. It's definitely a shortcut, but I can help you with the formula too. Alright, to reject or not reject, critical value is at 9.210. Our test value, though, 8.046, that's going to fall in the non-shaded region this time. So we do not reject that null hypothesis. And again, null hypothesis is our claim. So now our third example that we get to, again, refresh ourselves on how do we word that summary. And we would say not enough evidence to reject the claim. That the proportions of those who will donate organs are equal. So again, when your null hypothesis is the claim, it's all about enough evidence to reject or not enough evidence to reject. We don't get to talk about supporting or not supporting that claim if the claim is in the null hypothesis. So just be careful on that one. Just be careful.